Okay, welcome back. What I want to do is continue with, again, Sitting Gills, electrotechnical technology. And again, we're still looking at level 3. Now remember that this is normally a 4-year course, okay? So there's a lot of work to be done in this case. And you cannot do it in 5 or 10 minutes. You need to apply yourself to the task in hand and put in the hours, okay? I can only speak for myself. I remember when I was trying to qualify as an electrician, and I said trying. It took me hours. I was working up until 3 a.m. in the mornings. Okay, some Saturdays I couldn't go out, but I had to stay in to do work. But I succeeded. Okay, and I went further than that. So it's not an easy step. It takes a lot of work, and you need to apply yourself to the task. Okay, let's commence. What I want to look at mainly is speed, poles, frequency, EMF, and magnetic field strength. Okay, that's my main interest for today lesson. Okay, let me just pan back, make sure we can get it all in. Okay, okay, and the outcome of this lesson is understand the function of electrical machines. Okay, that's what I'm looking at. Right, so for today's outcome, the student will be able to describe the interdependence of frequency, speed, pole per phase, EMF, electromotive force, speeds, and magnetic field strength. Okay, and this is what I am looking at here. Okay, in case you're wondering what I'm reading from. And yes, there was additional notes in there as well. Okay, let's pan back, make sure we get it all in full view. Okay. Okay. Now here I'm just going to keep this at overall distance, but let me just move in a little bit so you can see what it's trying to say. Okay, I'll move along. Okay. Okay. Hopefully you're going to read this for yourselves. Okay, and I'm not going to read this out to you at all. You'll read this for yourselves. Okay. Come back. Make sure we get it in full view. Now remember, you can zoom in on your when you view this on the YouTube. Okay. Okay. I'm leaving it there for a moment. Just extract. Series motors are able to start up on the load, but must never be run unloaded. The reason for that is that they will burn out. Shunt wound motors are constant speed machines, but cannot start against load. Okay. So those are little notes to bear in mind. Okay. Factor that affect the way in which motor works. Okay. The rate at which a rotor turns depends on the synchronous speed of the rotating magnetic field. This depends on the frequency, pairs of poles, the amount of slip. Now you will always have slip in a motor. You must have slip for the motor to be rotating. Okay, and on average the slip is about 5%. Okay, but that is not fixed. Look at the rating of any motor and it will tell you what the slip percentage is. Okay, just to make sure we have this in full frame. Okay, now synchronous speed. Right. The speed of rotating magnetic field is directly related to frequency, the number of poles. Okay, frequency. This tells us how many times the supply changes direction in a second. Poles. In a two-pole motor, the poles will be 180 degrees apart. That means that in a two-pole motor you have one pair of poles, and the flux changes direction every half cycle. In a four-pole motor, the flux moves 90 degrees and takes two cycles to make a complete turn. Here you have, if it's four poles, then you have two pairs per pole. Okay. Changing the number of poles has a significant effect on the speed of the machine. Speed is labeled as N and is measured in revolutions per second, revs per second, or revs per second, or whichever rs to the minus 1. Frequency is labeled F and is measured in hertz. The number of poles that exist are considered as pairs of poles. Six-pole motor has 3 pairs of poles. Okay, and here we have N equals F over P, where N equals speed, F equals frequency, and P equals pairs of poles. Okay, let me just pan back so we get that in full view, and then I'm going to move in so we can see it in full. Okay, and make sure you can read this as well. Okay. Okay. I'm just making sure that you can see it and read it for yourselves, okay? Basically, that's all I'm trying to ensure, that it's in frame and that you can see it in full. Here you have the N equal to F over P. Now here, remember that this you can transpose for P, which will then equal F over N, okay? And to find the frequency, it will be simply be N times P, okay? Overall, in regards to transposition. Okay. Okay, just trying to make sure it's in frame, and I'm going to pan out just to make sure that we get everything in view. Okay, and we'll hold it there for now. Okay, thank you. Okay, good. Now you need to write this out again for yourselves. You need to apply safety, safety, safety every time. Okay. And whenever you're dealing with motors, you have to ensure that if you're working on motors, that those motors are isolated safely and they cannot be turned on by accident by anyone else. So all fuses must be returned, must be removed. Any switching that is applicable should be locked off, and only you who has the key. So again, safety, safety, safety. Okay. Now slip. Slip is the difference between the speed of the rotating magnetic field and the speed of the motor. Now here, remember that the motor speed will not actually catch up to the electromagnetic field. It will lag behind it by some degree. If the rotor were to speed up to synchronous speed, there would be no difference between the rotating magnetic field and the rotor. This means there would be no induced EMF. If there is no induced EMF, there is no induced current. Without the induced current, there can be no second magnetic field. No interaction between magnetic fields equals no movement. Okay, so there will not be any movement. The motor will simply, it won't rotate. So you must have this difference between the slip, the motor, and the electromagnetic field itself, which we call slip. And we can determine the slip by a given percentage, whether it's 5% slip, 3% slip, etc. Okay. Let me just pan back a bit, okay, so we can get it in full screen. Okay, yes. And let's just go on so we can get this into view as well here. Okay. Okay, yes. Okay, thank you. Let's go back up. Okay, make sure we're back in frame. Okay, and I'll pan back a bit so we make sure we have it in full view. Okay, thank you. Right. Now all these videos links into each other. Okay, they're not separate entities. They have a link to each other. Okay, they're not separate. Okay, but I just need to make sure that you understand that concept as such. Oh, okay, sorry, I'm a little bit out there. Okay, let's just make sure it's in frame. Okay, yeah. Okay. Change in EMF, right. Now there is a different direct relationship between the applied voltage and the torque turning force developed by the motor. This is not linear. As the voltage halves, so does the torque. In reality, the torque varies as a square of the voltage, and you've seen this already previously in one of the videos which I did. Torque equals voltage squared. But also remember that torque can also equal the amount of current. You can increase the torque by increasing the current also within the circuit, providing you have your given supplied voltage. Okay? And it depends on what control is being implemented to control the motor, whether it is resistive or a electronic system of control. Okay. Let's make sure you can read this. Right in full, across in full. Okay. I'll turn back and you can see that. Okay. T torque equals infinity squared. Infinity times voltage squared, I should say. Sorry. But again, check your electrical principles, look it up, make sure you have the correct formula, the correct application and how it has been applied. Okay, do not just take it as read. Because I may make mistakes, I could be wrong, okay, but I try my best to make sure that it's compatible with regards to the electrical institution of knowledge which is applicable in the electrical electronics engineering spectrum. Okay, I think that's in view. Okay, that's in. I can take that as okay, magnetic field strength. Okay, and here again, I'm just going to leave this for you to read for yourselves. In any AC induction motor, there are a series of conditions that are met. A voltage is induced in each conductor. The voltage produces an induced current, the rotating magnetic field, and the magnetic field generated, etc. The force always acts in a direction to drag the conductor along the rotating magnetic field. If the magnetic flux density were to change, then there would be a significant change in the force exerted on the conductors. And that's just in brief. Okay. Okay. I hope you found this useful. Again, extract the information, make notes for yourself. Do not take it as read. Okay, you will not learn it all from the screen. You must go away and do some work in practice. You must put pen to paper. And I repeat, pen to paper. Okay, thank you. Have a good day. Bye-bye.